So let's just jump right in. First thing I wanted to say, because I've talked to a few people in the last day, and it's a hardware synth. And I guess we're at a software developers conference, so it is a hardware synth that's right here, and we'll do a couple demos during the talk. The talk is about the synthesis or the oscillator itself. It's not. I tried not to make it a sales pitch about the synth. It's actually about the engine. Would love to take questions during the talk, so feel free to interrupt at any point. And if I'm going to address it, I'll just let you know that we'll cut to that in a slide or two. But feel free to interact. It's much easier that way. Okay, so I'm Steve, was just introduced, so you don't need any more of that. My business partner is Daryl McGee. We founded the company about 9 years ago. Justin, who's actually here, is our lead software developer for the DSP and the synth engine, and the rest of the guys are honorable mentions. Okay, so in about 5 years ago, I had a dream about, well, I was thinking about how wavetables work, and I was trying to work out the math. And I'm going through my head, and you can read all this stuff, but the salient thing is, if you want to play an A440 across a wavetable, you need 109 samples approximately. And it means you're jumping about every 18.7th sample, and it gets kind of messy in your head. And I started getting a little dizzy, and because I'm a more visual thinker than I am a math thinker. And so I started daydreaming about, well, what would happen is if I took that playhead and rotated it? And then I said, well, what would happen if you changed the shape of it? Instead of a line, you traverse the wavetable with a circle. These are the waveforms underneath that would result in. And then essentially what happened in my brain is I sort of thought of this thing as a surface, not a series of samples, single cycle samples. And so this is sort of the representation that the wavetable is very much just a collection of samples or morphed samples. And a terrain is actually a mesh in space that has elevation. And we'll just keep going. So I thought I invented this new terrific synthesis, and of course I did some research and found out that there's a zillion of papers, academic papers written on it. There was my heart sank when I first saw Aaron. Aaron has an example on YouTube. It's this middle one up here, is exactly in my head, in my mind's eye, what I was imagining it would be. It's funny, there's a guy named Curtis Rhodes. He's got this famous book called The Computer Music Tutorial. I contacted Aaron, and Aaron actually was studying under Curtis in California. And now I believe I just saw this this thing called Contrast. It's a software version of Terrain Synth that came out like literally 6 weeks ago or so. And Peter V is the head of this project, and I think Aaron is actually working with Peter. So it's kind of a fun world where everybody is interlocked. But there's plenty of stuff going on in this world, even though it seems like nobody's heard of it. There's also a really cool iOS app. It's not a synthesizer, it's more of a LFO modulator, or I'm sorry, it's a sequencer. And it's the same kind of idea where you traverse a terrain and it creates notes based on the elevation as opposed to samples. The earliest I saw was Richard Gold, and I was perplexed because this was 79 from Byte magazine. In the back of the article had the source code. I think it was assembly, and the computer he was running couldn't actually generate the really simple math for just one waveform fast enough to actually play it. So he generated the output and then used, I don't know how he got from point A to point B, but he used it in creating some music. But it was a 16, this is the actual data in hex. It was a 16 by 16 sample terrain. It literally looks like this. And of course, if you try to traverse that with any kind of path, you're not going to get a very nice waveform. It's going to look like that. So in the synth, we actually upsampled this, and we have a terrain, and maybe we'll get to see that in a minute. So Wavetable has some lingo. I just kind of wanted to define that, and then the lingo for Wavetables has some lingo, and wave terrain has some lingo, and I just wanted to differentiate that so as I'm speaking, we can be on the same page. I was a bit confused because in some literature I've read about wavetables that each waveform was a wavetable, and I guess it is a table of sorts because it's a collection of samples. But when I speak of a wavetable, I'm speaking of the whole collection. I've also heard them called frames, or waveforms. So you'll hear me probably call them waveforms as I speak. And the thing that I call a playhead, I'm not sure there's actually a name for, but what I'm referring to is actually traversing across. In wave terrain, the whole thing is the terrain, and I call what I call playhead in a wavetable, I call a path. And in some of the literature, it's referred to as trajectory, but that's really a long word to put on a synth GUI, so I just chose to use the word path. And in this case, it would be a line path. So in our implementation of the synthesizer, I'm telling you this because when you see visuals, you can get straight in what you're looking at. We have all kinds of ways of colorizing the data in the terrain. So these are just color variants. It has nothing to do with the sound. And then there's also ways of viewing that data from top-down methods. These are more topographical across the top. We have that mode. I find that is quite useful when the path is complex. If you're using like a star shape or something like that and you have it rotated at some isometric view, it's kind of hard to tell where exactly it's aligned with the data in the table. And then these are the isometric ones. I chose to make it look like this as opposed to using modern rendering techniques because I wanted it to look a little retro. But so that's what. And this one this is the latest one that we chose to add because it looks more like a wave table. And when you're playing it with a line path, it actually is a wave table. Okay, so now let's talk about the terrain types. So there are 3 types of terrains that we support in our engine. One is a mathematical terrain or procedural terrain. I'm stealing the word procedural from the procedural texture map in 3D graphics rendering. The other one is images. Obviously, that's me, and that's what the terrain would look like if you were to play my face. Our tagline initially was "Play your grandma's face," and it's kind of silly, but anyway, we put that up there, and then we also, and I'll talk more about each one of these, and we also will import wavetables. Oh, and so when the wavetable looks like this, you can render it to make it look like a terrain. Okay, so these are some examples of our terrains. The procedural ones. What's interesting about the procedural ones is that someone asked me yesterday, does that mean that it's sort of like analog? Well, of course it's not, because it's, oh, that's just gotta be, okay, I thought that was a fire alarm. It's probably a juice class next door. Okay, so what's interesting about these is because they're mathematically based, in the first slide, I mentioned that you needed 109 samples and you would hop like every 18.77th sample, and then you have to lerp between this. And so on these mathematical ones, you don't have to do that because they're floating point. So when when you're traversing the path and it dictates an X and Y point on that terrain, that exact point, that floating point X and Y are gonna give you an exact value. You don't have to lerp. And that's kind of interesting because that means it's a smooth waveform. It's not quantized in samples. Also, what's worth noting is some of them are Cartesian in nature, like the top one. and some of them are more polar coordinate in nature. And so why I'm describing these is because as we've been taking this journey and productizing this concept of a terrain synthesizer, some of these things have been emergent in thinking, right? You don't think about this stuff immediately. In other words, if your path is generally a closed path, then you're more sampling in a polar coordinate manner than you are in a Cartesian manner. And so, hence the idea, and we'll show that in a minute. So this guy is polar coordinate, and I'll give you some more examples about this stuff, but I just wanted to point that out. Okay, so this terrain is based on this equation, this generalized equation, z equals sine x times sine y, with the boundaries of -1 to 1 in both directions. One of the interesting things to do is to generalize the sine wave with a generic waveform. So I created a waveform called wave, and the m variable in the argument list is a floating point variable that morphs through 4 different waveforms. So these are going to be easier to see, but I just wanted to point that out. Also, what's fun about this is that in a wavetable, the table's static, right? You import samples, and that's what you get. In terrain synthesis, when it's a procedural terrain or a mathematically based terrain, the parameters of the equations can be modified live, which means those become targets for modulators like LFOs and envelopes, and expressiveness like aftertouch and velocity and pedals and such. So the reason why I'm bringing this math up is because all of these variables in these equations become targets for modulators. Right. Okay. So this is where I was going with that wave function thing. Okay. So this is all the same terrain being modified. The first 4, the top 3, and this one over here is that m variable. So I'm morphing between a sine wave, a sawtooth, a square, and triangle. And they literally morph. It's not an int. It's a float. And then there were 2 others. This is just a stretching of the stretching of the frequency in x. And this is a scrunching of the frequency in y. And this terrain is the terrain that I was referring to earlier that I said was more of a polar coordinate. Remember when I was referring to the way to look at, we have different visualizations in the implementation. This is a good example of that. So this is the visualization in the 3D grid, obviously. These visualizations are the top down. And you could see that the shape of the actual terrain is less understandable in this view than that view. However, the idea of what happens when you trace this terrain using the path, it becomes more visually understandable. You'll see that the green circle in the middle is getting larger as I go through, and the yellow waveform on top is the result of traversing that path. So you'll get a single cycle sawtooth here, a double, triple, and so on. And I think this is a good time to, let's see. Yeah, this is a good time to give a little demo. So if we could switch to the synth. Is anyone, oh, good, thank you. That's cool. I am Oz. Okay, right, so here's this is the actual user interface of the synth. And that's playing it. And we could switch to a different view. So that's the different views we were looking at. And we can change the size of, is this too loud? Is this too loud for everybody? It's okay? Yeah, okay. Let me turn it down a little bit. And so you can, if you want, you can just modulate this with an envelope. And these are the kinds of things you get, which is mind-blowing. I get to see some faces out there. So this is the cool thing. Now, a thing you learn very quickly, though I learned, is that when you're making a synthesizer, that the waveform itself is actually quite boring, and you can create the most cool-looking waveforms, because obviously you can do that with this. You can load pictures and do anything. It's not the waveform that is what's interesting to your ear. It's the changing of the waveform which is interesting to your ear. And I think what terrain synthesis brings to the party is a zillion variables and variations in the way you can modulate and transform waveforms in one way to another. In a wavetable, you literally only have one axis of freedom, and that is just moving across the table in one direction. In this one, and when you go off axis, meaning if we change the position, and again, we can modulate all that, right? So I can just stick an LFO on the position. There we go. So you could so there's lots of cool things you could do. And so that's that. Okay, switch back, please. Thank you. All right. So that's what this sounds like. All right, so those were the mathematical. So I'm going to transition now from the mathematical terrains to the image terrain. So is there any questions on that? No? Okay. All right, so it's funny, I was reviewing these slides and thinking there are no images like photos in this. And I was wondering why I didn't do that, and I thought, well, that's a good point to discuss. So I can show you a demo of images. We'll do that in a minute. But it turns out that if you play an image, it just sounds like noise, because the image is full of crazy changing, adjacent pixels. And this is a funny psychoacoustic, I don't know if that's the right term, but your brain does funny things, because when I tell people about the synthesizer and that you can bring an image in, they immediately jump to, oh my gosh, we can bring in pictures of the Grand Canyon, or NASA photos of Mars, or their brains, and it is totally that was my first reaction to this. This is going to be great. I can bring photos of my grandma's face. It turns out that those pictures, like I said, are rather noisy in general. They're fun to play with. It doesn't mean you shouldn't do it. But what turned out to be more interesting sonically or harmonically are bringing in pictures that are basically gradients. Because after all, if you think about what a waveform would look like in an image, it would just look like a gradient. A sawtooth is just black to white. And so arranging the gradients in various ways gets you the most sonically rich and harmonically rich terrains. So these grayscale ones were all done with AI, because I got tired of trying to draw them in a paint program. And of course, everybody's talking about AI, so I thought I would give it a whirl. And I didn't use it much, but I created some prompts. It took a few iterations of prompting, but I told it, what I wanted was a polar coordinate grouping of sonically rich gradients, yada, 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 and then it created these for me. This one looks so blurry, but what's cool is that instead of it being like, this one's more ring-like, and you can imagine that if you play a circle over that, and as you traverse, as you go from ring to ring, you'll get a very distinct chop, almost like a PPG going through the wavetable on a PPG. This one is essentially morphed between the rings. So can we switch again? Oh, great. Okay. So we'll go over here, and so these are, by the way, these are all the math terrains that we have, and then we come down here into the terrains that are images. And so let me see if I can find that terrain. Okay, so yeah, here's one. This one looks blurred between it, but we'll give it a whirl. So as I hit a note and make the path size. And then in the middle, in the very middle, it jumps to a. So again, this is, you know, and you don't need to be in the center, so you can play across the waveforms. Okay, we can switch back. Thank you. Right, so that's what these sort of sound like. We had to do something with the different color channels of the images. So, you know, an image is actually nominally three different images. There's a red image, a blue image, and a green image. And when we put them all together, our eyes see a color photo. But when you're reading, just, you know, literally reading the data from an image, you have to make a choice of which of these color channels you're going to read. And so what's really interesting is that you can choose an R, a G, or a B value out of the image and use that as your terrain. So what happens is a color image becomes actually three terrains in one. And that's why you see this very weird thing here where you see this kind of shape. I think that's the blue, and then the red has different, and the green is different yet again. And we can morph between the color channels. So what I did was, how I actually created these is I created AI versions of what I asked it to do as harmonically rich gradients. And then I took three of them and asked it to combine it in RG and B channels. And so these are the resulting images for that. And, oh, I see, the next slide is great. Okay, so if we look at this image, which are four bands of kind of color rainbowy things, these three across the bottom are the resultant terrains from that image. So you can see they're quite a bit different. And the fourth one up top here is a grayscale luminance value, which is some mathematical combination of these with various, I can't remember off the top of my head what they are, but the scalar for each one is slightly different. They're not equally scaled. Yeah. Any questions on that? No? Okay. Quiet crowd today. This is just, I just described all of this, but this is just a slide that shows if you put your ring in these positions, what waveforms you would have. What time is it? Am I going really fast?
You're 9:24.
Okay, good. That means at the end we could just play with the synth some and hear it. Okay, right. So so that's it for images. No question. Okay, the third type I mentioned. Oh, we do have a question. Great. Perfect. I'm going to come to that. So, in fact, right now I'm going to come to that. Good question. So our internal representation, I paid that guy a banana before the show. The train size is 512 by 512. And I do understand that 2048 is kind of the common serum format. So yes, we do have a reduction. So let me just start at the top. So when we import the wave file, which is nominally the wavetable, does everybody understand how the wavetable? Okay, I figured this crowd would get that sort of thing. So when we bring in the wave file and chump it up into waveforms, it can be any number of waveforms up to 256 frames inside of that wave file. And so what that means is we need to shrink the length of the of the waveform down to 512. So we're doing a reduction of quality essentially. And in the Y, we're going to expand that 256 to 512, but it doesn't have to be 256. In fact, often wavetables are less than that, and the application will do a morph, internal morph between those waveforms. Sometimes they're only like literally single digit, but we'll stretch that out. So I'm going to shift away from terrains now and start talking about paths. So are there any more terrain questions? Yes. I'm sorry? Aliasing, yes. We have a slide at the end. Yeah, that's a great. This is an aliasing machine before it's a synthesizer. Justin, that was the first thing he fixed, yes. Okay, so on to path. Oh, I'm sorry, I can't hardly see anybody. Was that the only question about path?
Yeah, it was last mentioned in the images, if you look at your experiment, we were also doing typical image processing on the images, so blurring them or also doing the kinds of transforms that you shift.
Correct. So it was a struggle for me not to want to add image modifiers in the synth itself because it seemed like it would be so natural to do that. You have a CPU budget. I'm just trying to focus this more on the engine itself as opposed to the instantiation of how we did our synthesizer. But I'll talk about that just for a minute. In our instantiation, we actually have 2 terrains per voice, and you can morph between them, and you can morph between a math one and an image one and a wavetable one. And so our CPU budget, there's also 4 timbres or 4 layers of synths in the synth. So it's actually 8, we have to load 8 terrains. And so that's the reason why we made it 512 by 512, because we don't have unlimited memory resources. And I did do some experimentation pre-processing. Yeah, sure. So what's fun about this is that, if you Justin, what's the name of the app that the standard audio app that people use? Does anybody, what's that? Audacity, thanks, right. So instead of having to go into Audacity or Serum or some app like that to create these things, it's a fun exploration because you can go into Photoshop or you can go into PowerPoint. In fact, I kind of think in PowerPoint because I worked at Intel for so long, it's kind of really messed up. But I use PowerPoint as my drawing application. I did a lot of just literally gradients in PowerPoint, and that's how I started to do a screenshot of that. Then I would bring it into some paint programs, and I messed around with various programs and blurring and stuff. And in fact, what blurring does is it's sort of a morph, right? That it's just it's actually more of from an audio point of view, it's a filter, because as you smooth off any high changes between adjacent pixels, that's essentially reducing the harmonic content. And so that's what ends up happening. And I think in that app that I showed down in this corner that came out a month or so ago, they actually have some very small image processing built into that app. You're not Peter, are you? No, okay. I was hoping to meet him. He actually emailed me, and I would love to meet him because we're like, yeah. Anyway, yeah. So there's a long list of stuff we want to do in the synth, and maybe we will add a blurring or some sort of affine transforms or whatever to the images. Okay, let's see. So on to shapes for terrains. I'm sorry, for paths. So these are all the shapes that we support. I'm sorry, I keep trying to get ahead of myself. One question is about continuity, waveform continuity. There's a good reason why the playhead of a wave table goes from left to right. And one of the sort of unspoken or spoken rules is to always make sure that your first and last samples are the same, or at least adjacent. And that is because if you don't, what happens is if you trace out your waveform, you'll always get this gap, this jump here at the end. And so no matter what your waveform looks like, it'll always sound similar to a sawtooth because of this jump. And so my first vision in my head of rotating it, was a little stymied because of this discontinuity problem. So that's why, when I said I was first started thinking about it, this actually came into my mind, and I thought about that's why a closed path is better, because essentially what happens is because your first sample is adjacent to your last sample in any closed path, you're gonna have continuity across the waveform. Everyone get that? Everyone? Yeah. Okay. So even though the paths are piecewise linear and not like C2 continuous. I got that from watching this really cool spline video. Everybody should see that. Yeah. So this one here, which the polygonal shape, even though there are corners in the path, those corners still are adjacent to each other. So you don't necessarily see where they are, although they actually may end up being here. But it doesn't cause a discontinuity, which gives you that leap. Lisa Jewell curves. I kind of want to take some of the woo out of this, because it turns out that you're in your mind's eye, like you'd want the Grand Canyon or pictures of Mars to sound ethereal or whatever. It's the same thing with these shapes. It turns out that the longer the path, it just means that you've got to traverse that path. The distance between the samples along that path just get bigger. And if they get bigger, that means the continuity between the points of that path are less continuous, which means you're going to get stuff that's more noisy. It's just going to go up and down. So the longer the path and the crazier the path, it turns out it's less sonically pleasing. It all degenerates into noise at some point. So when you first start playing with the synth, you might want to make a big path and move it crazily and fast. But it turns out that a smaller path moving gently across a terrain is actually more sonically, not necessarily pleasing like pleasing music, but it's more harmonically consistent. Okay, right. Okay, so these are just different types of paths. I'm going to talk for a minute about traversing these paths and collecting the points in a moment. And it's good to note that there are a difference between a path that's generated with a polygon path, which is generated by line segments, versus a continuous path that's generally like variations of sine waves and such. Okay, also the paths can be affine transformed. So this one is this was a square path, and it's squished. Once you squish it and it has eccentricity, then you can rotate it. And also the Lisa Jewell ones, we also have a knob for phase, so it gives you that classic spinning oscilloscope thing. And I'll show you all these in a second. Right. So how do you collect how do you collect the samples, and how do you understand where to do that? Okay, so when you're using a path like a circle, it makes a lot of sense to collect the dots in a polar way, meaning that you're incrementing the angle that you're sampling through. As opposed to a line segment, you're not going to have parametric equations to describe this as easily. You have x and y coordinates of each of the legs of the polygon, and that you can lerp through those. And we'll get to that a little bit more in a moment. Okay, so I didn't rearrange these, so we're going to do this one first, right? Okay, so because the equation of this path is essentially x and y as a parametric equation, and you have your amplitude scalars a and b, As you rotate through one full revolution, you will rotate through the entire length of the path. Determining the line, the arc length of any random line turns out to be non-trivial. It's what is it? The integral of some Pythagorean theorem thing. I don't want to get into all the details of that, but calculating that on the fly, because because all of these things are in motion, because they can all be modulated, you can't pre-calculate what the position is of your XY samples on the fly as easily. So I decided to use the concept of sweeping an arc. So again, if I needed 109 samples, here we go. I would divide 2 pi by the 109 floating point version. And then I would know how many radians to increase my sample, put those into my X and Y, into my theta of the parametric equation. And out comes my X and Y. And once I get my X and Y, then I just go to my terrain and I say, okay, what's the height of the terrain at that X and Y value? I can't wait to the end because there's some really fun things you could do with the points. Just little. Okay. All right. So we sweep through these parametric equations using polar coordinates as opposed to Cartesian. If we were to try to sweep through a square path using that technique, what happens is, and this might be intuitive to some of you, but I thought I'd point it out, that I took little screenshots of this and made them bigger. You could see the distance between, okay, these are equally spaced by calculating it by lerping from the first point to the second point of each line segment. So these are evenly spaced all the way around. If I were to use an angle to sweep it, what would happen is what happens when they're evenly spaced is that your angle changes over time. You notice this angle is bigger than this angle here. That's the point of showing this. So you can't sweep a polygon using polar coordinates. Otherwise, you will get a equal distant samples around the exterior. I'm sorry I'm making such a mess of this. Are you guys catching what I'm trying to? Okay. Kind of nerve-wracking. Okay. So now I'm going to mess this one up even worse. Okay. So now when you do have to calculate around a polygon, it's easier to do some complicated calculations of which segment am I in. You can calculate the length of the square, obviously, right? It's 4s or whatever, right? So as you sweep through the, if you normalize going around your path from 0 to 1, you could tell that, as I get to, if I start up there, S0, it would be, X1, Y1 would be 0.25 of the way around, and this would be halfway around and 3/4 of the round, and that's fully around. So I can do some very simple math. I know the lengths of all my segments, and I can calculate which segment I'm in. And once I figure out which segment I'm in, then I can lerp between the X and Y points between the segments to get an equidistant number of samples. So it turns out that it's not just a super trivial thing. I think when we started this, I just used sweeping theta around, and I realized that I was not creating equidistant samples. All right, good, got through that part. All right, let's see. What happens when your path collides with the edge of the terrain? There's a couple of choices you can make. You could just hard limit it to the edge value. You could jump around to the other side, or you could reflect. And we chose to reflect mainly because these waveforms aren't accurate. I actually just kind of drew some funny lines in there just to sort of depict what would happen. But obviously, somewhere along this waveform, when you hit the edge, you're just going to get a flat point. This one, you can get this giant discontinuity because the other side isn't necessarily reflective of this side. But when you reflect, then it's going to be more continuous because it's a similar data, especially right at the point where the reflection happens on the edge. So that's the method that we chose. 10 minutes, okay. Right, good, I'm almost done. Let's see, right, so one of the also fun things that I discovered during the creating of this was that if you just take an inclined plane and you run a circle around it, it creates a sine wave. If you have a stepped plane, you get a square wave. If you choose to move the path in Y, you get pulse width modulation, right? This little kind of a corkscrew terrain gives you a saw. This thing gives you a organ with any stops you want, because essentially as you move your path around on a terrain like this, you're just going to get all these funny sine waves that get additive sine waves. And then this just gives you some triangular shapes. It's kind of hard to know. Okay, there's the alias question. Okay, everybody knows what aliasing is in here? Okay, this is a really quick description of that. If you take a sample too slowly of a signal, what ends up happening is you don't have enough samples to reproduce the signal, and you'll make this slower sine wave. And in this instance, this sine wave is 5 times slower. And so what'll happen is that you'll get this lower tone. Okay, so anyway, what happens is you'll just get noise. This is the bottom line with aliasing. Am I good now? Oh, good, I'm back. Okay, crazy. Okay, so when you have a terrain synth, boy, the terrain, especially when you bring an image in, and we keep talking about it being really noisy, those high frequency changes means you're going to have a lot of high frequency data in there. If you try to sample that data around the path, what'll end up happening is you're absolutely going to alias, because you're only sampling to hit a certain note, and we only have so much bandwidth in terms of our choice of like 48K sampling rate. So we did this little funny thing where whenever we take, I'm going to kind of smurf through this because it's kind of complicated, but whenever you are about to take the sample, we take the sample, essentially Justin's going to correct me here, but it's kind of like oversampling for that particular note. And then we run it through an FFT, we do a brick wall filter, and we invert FFT it, and that's how we fix the sampling. Someone asked that the aliasing, someone asked that question. What's interesting is because you don't know what the waveform is until you know where the path is on top of the waveform, so you have to do it every time. It's not like a wavetable where you can pre-calculate a bandwidth limited waveform and then make 8 tables, 1 for each octave or something like that, because everything's dynamic. You have to do it on the fly. That's another reason why at some point you just run out of CPU. And probably another reason why terrain synthesis hasn't been introduced yet, because with a Raspberry Pi 5, you've got a lot of CPU. With 10 years ago, you could never do this. And I put this giant switch here because when I started playing the aliasing, it was like, that's fun. So we actually have a way to turn anti-aliasing off, and you could it's crazy. If we have enough time, I'll try to get to that. 4 minutes, okay, let's get to it quick, okay. This is the fun part that I wanted to get to. So everyone knows what oscillator sync is in the room. One period of a master oscillator will dictate where the slave oscillator has to stop. Well, when you do terrain synthesis, the master oscillator is just one loop around your path. So if you take more than one loop, like 1.42 loops around, this waveform will wrap and start making itself again, but then you stop it. And so what happens is you get that waveform. At the 2.5, you get the same idea, but I'm going around 2.5 times for every time I'm supposed to go around once. So you just multiply the phase angle by 2.5, and that gets you an oscillator sync. I thought that was really interesting that some of these things that are in analog synthesis are created by multiple oscillators, that you could do it just with a math game. The other little math game was phase distortion. I wanted to say this a few slides ago, but I kept trying not to. If you crunch the points closer together in some areas and further apart in other areas along the path, you're basically doing phase distortion. And so what I was trying not to say earlier is if you use polar coordinates to do a polygon, the corners will be phase distorted because the points will be closer together as opposed to evenly spaced. And so you can use that to your advantage. And now I think that is the last slide. Okay, so I'm gonna, for the last couple minutes, maybe, could we switch over, please? Great, thank you. So we'll just init the synth. I'll do a, okay, so now if we go over to the phase, or we'll do oscillator sync for, we'll do phase distortion. So if I play a note and so you can see, I don't know, can you see that? Yeah. If you look at the black dots up here are just visual representations. They're not actually the number of samples, as is the spinning thing, right? Obviously, you would have to go 440 times for an A note in 1 second. You wouldn't see it. But it does go slow with slow notes. And you see how it's accelerating? It's actually showing you the phase distortion as it accelerates. And then the high notes goes a little faster. Yep. Okay, and then I wanted to, 1 minute, okay. And then I wanted to point out oscillator sync. Let's see, so we'll bring this back to 0. And then here. And you can see when I go less than the full path, you could visually see it. And then as I wrap around, so you can do some really fun stuff here, and I guess that's a wrap. But if you have any questions, thank you. Thanks.